You can only use this limit definition. And we've done ones just like this, right? Yeah. Done ones just like this. So one thing that's nice is what's one thing that cancels up there? The ones do cancel, right? And you're just left with this thing. What are you going to have to use? You're going to have to make a what? A table. You have to make a table. So what does it look like it's getting infinitely close to when you make that table? One. Do you have a specific question about any of the algebra they did?
No, I was just off about it.
You're just off? Yeah.
How does it trig? We have to know like trig values.
You need to know your basic trig values. Yes, you need to know your basic trig values, and it will show if you don't. Something is better than nothing. But when I say basic trig values, you really only need to memorize the first quadrant. If you memorize the first quadrant, then you're pretty much all set. What's that first angle value you need to memorize? Pi over what?
2.
Nope.
Pi over 4.
Pi over 4. So this is pi over 4, right? What point is pi over 4? What point is right there? Root 2 over 2, comma, root 2 over 2. There's also, what's this one? Pi over what? 6. And do you remember the point there? Root 3 over 2, comma, 1/2. And then what's this one right here? Pi over what? No, pi over 2 is here. Pi over 3. Do you remember what pi over 3 is? What's pi over 3?
1/2.
Yeah, 1/2, comma, root 3 over 2. No, this is just the points on the unit circle. And then you remember, so, ka, toa. Remember that? Remember that, everybody? Yes, you took trig, so, ka, toa, right? So then you can derive, not the derivative, but you can figure out the trig values in each of those. Because what is sine? That's opposite over hypotenuse. And this is adjacent over hypotenuse. And this is opposite over adjacent. And all of these, what's the radius of the unit circle? It's called the unit circle. What's the radius of the unit circle? 1. It's 1. The radius is 1 on all of these, right? So you think of all of these as triangles right here. So look at that triangle right there for pi over 6. Cosine is adjacent over hypotenuse. So what's the length of the adjacent side for pi over 6? What's the length of the adjacent side for pi over 6?
1.
No, that's the hypotenuse. 1 is the hypotenuse for all of them. What's the length of this side right here for all of them? It's not for all of them, for that angle right there, for pi over 6. What? Over.
2.
It's literally on the board right there. That's the distance. It's the x-coordinate, right? The entire thing, root 3 over 2. So what is cosine? What is cosine of pi over 6? What's cosine of pi over 6? I literally just had Noah say it out loud. Root 3 over 2. Adjacent over, so adjacent over hypotenuse. Root 3 over 2 over 1 is just root 3 over 2. What's sine of pi over 6? What's sine of pi over 6? There's only 2 numbers. What's sine of pi over 6?
1 over, oh, no. 2 over 1.
No. No. Here's the angle right here. What's the opposite side?
1/2.
1/2. 1/2 over 1 is 1/2. Yes. Okay. What's cosine of pi over 4? This should be instantaneous. All of you, if this isn't instantaneous, study your trig or it's going to come really back to haunt you. What is it? Root 2 over 2. And what's sine? Sorry, root 2 over 2. And what's sine of pi over 4? Yes. Do you understand where these are coming from, everybody? Do you see the triangles that are there? Okay, so what about this triangle right here, yellow one? It's going to be green down there, I think. That yellow one right there, that's pi over 3. What's cosine of pi over 3? What's the adjacent side length of that triangle? 1/2. Done. What's the sine of pi over 3? What? Root 3 over 2. Exactly. You need to know these cold, like instantly, or it'll be very hard for you to do major portions of this class. So all of the other trig values are just reflections. They're just reflections of all of those things. You have to memorize them. You have to memorize them. You have to memorize them. Yes, Arvin?
So if it wasn't a unit circle, the radius was 2.
What's here? The negative 2, so that cancels the denominator and makes it negative root 3 plus 1. So there's your point right here. There's your point. Cool. Okay, any others?
Larger.
It's getting larger. What's happening to the function as you go further to the right? What do you suspect is going on here? You looked at the answer key, I'd imagine, right? Because you got stuck and you looked at the answer key. What's the difference between the green and the red right there? Not much. It looks like it's nothing, right? So in this case, it looks like the function is its own what? Yes. In this case right here, this is the one function that is its derivative. I'll just tell you what it is because it's going to come up later. It's y equals e to the x. The derivative of y equals e to the x is e to the x. It's really cool. At any given x value, the output is also equal to the rate of change at that point. It's pretty cool. It's really, really cool. But it's one that you will come to love because later in math, in calculus in particular, you're going to have to take repeated derivatives. And sometimes when you take derivatives, they go to 0 and then you're done. Just what's the derivative of 0? 0, 0. Well, sometimes they get worse. Well, what's the derivative of e to the x? E to the x. What's the second derivative of e to the x? E to the x. It just stays at e to the x. It's really helpful. It's really cool. But this is a great thing to ask about. We will prove that later, but not now. If the derivative is always negative, it means that it's always sloping what? It's always sloping down. So it's saying that the derivative is decreasing, meaning it's getting steeper. It's getting steeper. So this thing means it has to go down and it's getting steeper. Is that one going down from left to right and is it getting steeper? Yeah, here's the thing. Since there's no other information available on this, where could this be? Could I move this up in anywhere, really? Yeah, I can move it up. I can move it down. Does that change the answer to this question? No, it is still decreasing. The derivative is always negative, meaning it's always it's always pointed downhill. And is it always getting steeper? Yes. And it's really good. What does that CC mean, by the way? Do you remember what that CC means? Concave down. That's a good thing to remember. So if the derivative is decreasing, it's concave down. If the derivative is increasing, it's what? Concave up. Yeah, like this one right here, the one we were just looking. Right, there it is. Increasing derivative means it's concave up, and it's always positive, so you know it's always going uphill. It's always going uphill. Okay, this is actually a really good one to transition from. The question here, you're right. Look, going in this direction, what is the derivative doing going backwards? It's getting more negative, right? It's getting a little bit more negative and a little bit more negative, you know, so there's -5, negative, something like that. There's no way to peg it here because you're estimating it, right? And it's the same thing over here. 1, 3, 5, 7.5, maybe 9 or 11, somewhere in there, right? But you don't know. It's kind of like asking, here's the thing, on some tests and quizzes, maybe you've seen before, it's like, what's the next number in the sequence? What's the next number? Well, the most potentially likely number is 9, but do you have any idea what the number could be? It's kind of like asking, here are 3 points. How many functions go through those 3 points, right? Like, you could draw how many? Literally how many? You could draw an infinite number of things that go through those points, right? You need more information to make it more definitive. So you pick something that stays, I don't know, in character, I guess. So technically, could the n ones be anything you want? Yes. Well, if it's a function, it can't double back, but go with the general trend. Those are good ones to ask about, though. Thanks for noticing that. In your opinion, what are the best ones to look at? The x-intercepts, exactly, because the x-intercepts of one are going to be where it's the what of the other. Oh, you froze it again? The x-intercepts of one are going to be what?
Even with the peaks of the other?
The peaks, where the derivative is 0 of the other, right? So let's just say you picked one, right? And you try to do a logical analysis. So let's say we pick the red one. Let's say we pick the red one as, oh, look at this. Is the derivative 0 right there? Does the function cross at 0 right there? Yeah, and if we did the red one right here, oh, it does cross right there as well. And does it cross right there? If you looked at that in inverse, if you flip that around, if blue was the function, let's say blue was the function, red would have to cross right there, does it?
Yeah, that's what I saw.
It doesn't, right? And if you do blue, if we do blue, I did this wrong, sorry. That just happened to be both, right? So this one goes down right there. But look, if, where else? Oh, like right, oh, wait. Which one's which then? Let's look at this. So which one do you think is the function? Which one?
I mean the red one.
The red one's the function? Because it crosses there, it crosses there, and it crosses there. But what about the blue one? It crosses there, right? It crosses there. Oh, but wait, what happens right here? It doesn't. Does it cross in 2 places?
Yeah.
Right here it does, but does that third one work?
No.
The third one doesn't work. So which one's the function?
The red one.
F of x equals the function. The red f of x, and then the blue is the what? F prime of x. Does that make sense, everybody? The rest should also match. All the other characteristics should match, right? All the other characteristics should match. Okay, well, let's go through it. Well, what about A? How do we feel about A? A is pretty good? It's 3. So when x is 0, what's y? This just means it passes through the point 0, 3, and it passes through the point what? Oh, thank you. Not 0, 5, 3, 5. 3, 5, that's fine. So 0, 3, and what? 3, 5. Do you agree with those 2 points? Yeah. So it says it is, we can use highlighters here. Using colors is a great thing to do on this. F prime of x is less than 0 and increasing for x is less than 0. So what does and increasing tell you? What does this increasing thing tell you? It's concave what? Up. So the derivative is 0 and it's concave up. So the derivative being 0 means is it going downhill or uphill? The derivative is negative, so it's what? Downhill. So it means for x, it's 4x less than 0. 4x less than 0. So all the way up until x is 0, it's going downhill and concave up. With your arm, show me downhill and concave up. With your arm, downhill and concave up. Downhill and concave up, right? It's going down and concave up. It's like this. This makes sense, right? It's going down and it's concave up, like it's a cup, right? So it's just this half of the cup. So what's that going to look like? Well, it's going to go down and concave up. Do you agree with that yellow right there? Do you agree that is the derivative negative on that yellow one? Is it going downhill from left to right?
Yeah.
Is it concave up? Yeah. Mm-hmm. Could it do a lot of other things? Could it be steeper? Could it be less steep? Absolutely. Okay, so what about C? The derivative is greater than 0 for x between 0 and 3. Okay, so it's greater than 0 between x and 3. Does it tell you anything about the concavity? No. So what could it do?
Go straight up. Not straight up, but diagonal.
Well, it could do anything you want. You just know it's going up. So could it be a line?
Yeah.
Sure. Well, let's make it a curve. Let's just continue with this curve. Could it do that?
Yeah.
Is the derivative positive from 0 to 3?
Yes.
Mm-hmm. And then it says it's less than 0 and decreasing for x greater than 3. What does the decreasing mean? Concave down. And then this thing right here, derivative less than 0 means uphill or downhill? Downhill. So what's that going to look like? Well, from right there, it's just going to go down. How's that look? Is that pretty good?
Yeah.
So could you smooth this out into one? Is this a quadratic?
No.
Quadratics either look like this or like this. What would this be at a minimum? This would be minimum of what? Cubic. Because how many turning points does it have? How many times does it turn? Turns twice, so it must be a cubic. If it have one turning point, it's at least a quadratic. No turning points means it's a what? A line. Does that make sense, everybody? Yeah. Okay. It's not bad. It's not bad. Do you feel okay about this? What's the only wiggle room? You could make these steeper or less steep. That blue part could be a straight line, right? Just, make it nice. I've had people try to make them as purposefully as nasty. Please don't do that. Please don't do that. Okay, it's frozen, right? Okay, so what about this one? We're going to change it up just a little bit. So you've taken the function and drawn the what? Derivative. What could you do instead? Oh, exciting. Are you really excited? I am so excited. I don't know what to do with my excitement right now. Yes. Okay, here you go. Ready? Unfreeze. There you go. So that is the derivative, not the function. That's the derivative, not the function.